We're going to talk briefly today about proofs, and it will be brief. Some notes about proofs, especially if you haven't done them in a while, or maybe this is your first upper level math course, so the math courses you've seen them in have been very minor where somebody's just presented them on the board. We're going to take a look at some details about proofs. In a proof, no unstated assumptions may be used. I think you guys probably realize that. I think sometimes we try and cheat and we put that in there and hope that somebody won't notice that we didn't really, argue that made sense in some fashion, but you can't have an unstated assumption. The following are 6 types of justifications that are allowed in a proof. So these would be the justifications that you would have to include for a stated assumption. The first one would be by hypothesis. Okay, so we're starting with what we began with, a hypothesis. By axiom, so something that's been we'll talk more about axioms later. I'll get to that in a minute. By theorem, lemma, proposition, or corollary. That third one there is actually things that we've previously proven. So you're allowed to use that as a justification for why a statement would be true in your proof. A definition, obviously, is a good justification. The definition says that perpendicular means this, so now I have this fact about these perpendicular lines. A previous step in your argument, so by step number 2 or by a step above, something like that. And using what we did in the last section, by rule of logic. Okay, so if you have the transitive property, you've got P implies Q and Q implies R. That's why, by a rule of logic or any of the others, that we can say that P implies R. For the most part, our proofs won't necessarily have numbers to them. We are not going to do this like high school geometry, right? A 2-column proof. But you should keep that in your mind, because the thing that's nice about 2-column proofs is that they give you some structured thinking, which forces you to put a reason in the reason column, right? And sometimes when we start working in paragraph kind of proofs, or just writing a paragraph down kind of a thing, we get a little bit sloppy and we forget the justification part of it. So that's what this is talking about. We're going to look at a few types of proofs. The first one is called a direct proof. In a direct proof, you begin with a hypothesis, and you use definitions, axioms, theorems, and rules of logic to deduce the conclusion. And here's a pretty straightforward example of one. We're not going to prove it. We're just going to talk about how the proof would look, why it is a direct proof, in other words. It says to prove that the sum of 2 even numbers is, I should say, an even number. So why does that happen? Does anyone have any ideas as to how you would think about that, showing that that would work? Let's first talk about what it means to be an even number. Give me some kind of a description or definition of what you believe even number means. Divisible by 2. Okay, so if it's divisible by 2, it's even. So if I took 2 divisible by 2 numbers, okay, and you could take an example. You can't use an example to prove something, but to justify it and think about how to prove it, you certainly could. 2 even numbers, 10 and 14. And you add them together. Do you always get another even number? You do, and that's what we're trying to prove, or at least think about proving in this argument. So if you were to express the number as an even number, is there a way to do that without using a specific value? 2x or 2n or 2 something, right? So yeah, that's a really good way of doing that. So if we were thinking about doing this and we had 2 even numbers, we might express one of them as 2x and one of them as 2y, right? All right, so what happens when I add 2x and 2y together? 2 and then x plus y. Yeah, okay, so if I were to take 2x plus 2y and I were to add them together, I would have 2 and then I'd have x plus y. So why in the world is that an even number? Because I have something with a factor of 2 in it, right? It's divisible by 2. So when we're thinking through this one, I haven't provided all justifications, I get that and everything. But we started with the assumption, I have two even numbers, and we went straight forward to the conclusion, oh look, when I add them together, I do in fact get another even number. That's a direct proof, starting with the hypothesis and proceeding through to the conclusion. Okay? Let's do another one. Contrapositives, we just talked about that a minute ago. Contrapositive means to take to switch the order and negate them. So a proof by contrapositive, to prove that P implies Q, instead we could prove that tilde Q implies tilde P. They're equivalent statements, and sometimes it's easier to do a proof like this. To start with the tilde Q and find that tilde P actually occurs. This is an example of one that you could use for a proof by contrapositive, or contraposition is how your book actually describes it. Contrapositive is how I've seen it done more frequently, but that's okay. Let n be an integer. Prove that if n squared is odd, then n is odd. Now, I kind of like the idea of assuming the opposite. We only have odd and even, okay? So it's totally okay to say that if I'm talking about doing this backwards, then I could talk about taking the end result, which says n is odd, and saying, let's assume it's not. It's actually even, okay? So if n is even, then it looks a lot like the first one we talked about above, doesn't it? If n is even, I can write it as something like 2x, right? And then what happens? I got it. Sorry, thanks. I meant to unlock it. All right, so if n is even, we can write it as 2x. And then what happens when we, sort of go backwards? If I try to do this backwards, what happens when I square n? If I took 2x and I squared it, what would I get? It would be 4x squared. And what kind of number is 4x squared? It's even, right? So I took the opposite of what I was trying to show and showed that that actually made the hypothesis opposite as well, the negation. And especially if you've already done an argument that's very similar by reversing it, that's sometimes a really nice fact to be able to use because you've seen yourself or you've done that process once before. All right, this third one is very similar to the second one. It's called a proof by contradiction, sometimes also called an RAA proof. So to prove that P implies Q, you assume that P is true and that the opposite of Q is also true. So P and tilde Q. And then you somehow, in the middle of what's going on, come up with some kind of a contradiction or an absurdity. That's where we get the RAA part of this. Something happens that you're like, well, that doesn't make logical sense. This is an example of one. I'm going to let you take a look at it in your book. We're not going to talk about it, but it says to prove that there is no rational number, P over Q, whose square is 2. So if we were to attempt to do this in an RAA style or a proof by contradiction style proof, we would assume the beginning part is true. We'd probably need to rewrite it in our mind, the implication, because it's not written directly there. And then we would assume that the conclusion is false. So what is the if-then statement that's present here? Prove that there's no rational number, P over Q, whose square is 2. I got to be able to write it in an if-then statement, or I'm not going to even be able to get anywhere, right?
PQ is a rational number, then its square is 2.
Okay, so let's try that. So you said if P over Q is a rational number, its square is 2. I don't think that's quite right. Remember in parentheses, it tells us what we're trying to show is that square root of 2 actually is irrational.
So could you say if the square root of 2 is a number, then it is not rational?
Okay, let's try that. If square root of 2 is a number, what'd you say next, Hannah?
It is not rational.
What do you guys think?
I feel like can like a number's too vague. It shouldn't be a specific type of.
Okay.
I don't know, it shouldn't sound right.
It does sound funny. I think the basic parts of your statement are okay. It sounds a little bit awkward. It's kind of like we did one with squares and, what was it? It was if we had a square, then it was a quadrilateral or something like that, and it sounded funny. Every square is a quadrilateral, I think is what we started with. We said if we have a square, if there is a square, if a square exists, something like that, it felt awkward. So how could we reword it to maybe make it sound better? I think the order is right, though, Hannah. That part looks good.
If it is rational, then it's not square root 2.
So you would actually say that we should change it around. I think that the order we have is right. I think that if we're starting with square root of 2,
Pretty sure they can include P over Q in that song.
like somewhere in this statement.
Yeah.
Sorry, I was still reading. Okay, how would you like to include it? Well, I mean, P over Q is the part where it's talking about rational, irrational. It's not as easy as it looks, is it? You feel like you should just be able to write it down. All right, let's actually talk about how the RAA part would work without worrying too much more about the language itself, because the structure is okay. It just sounds a little funny when we think about it in our English language. But this part would be P. We've got the number square root of 2. So maybe you would want to say, Matt, maybe you could say something like, if I'm given square root of 2, then it is not rational, or something like that. Maybe something like that would be better. This is P. I have the number square root of 2. It is a number, right? It is something. And we're trying to say it is not rational. So what would we use as our pieces of our argument according to this? Not ifs and thens, but it's an and statement. Take a look up here. Whoops. Sorry about that. It's actually an and statement. I don't have it written with the and symbol between it, but we would assume that square root of 2 is a number, or that we were given we started with square root of 2, and we would assume that it is rational. Okay, that's what an RAA proof would look like. We take the hypothesis part and assume it's true, and we take the conclusion part and we assume it's false, and we come up with something in the middle there that doesn't work. All right, that's what RAA style proofs do. All right, the last one is proof by cases. There are times when this can be quite useful, obviously times when it's not going to be as well. So we had to list out all the possibilities and examine each possibility. So for instance, if one of 3 things has to be true and you can show that 2 of them are not true, then the third one must be true, right? Because there's only 3 possibilities, or however many that there are. And then, I think I said this is the last one, I totally lied, there's one more. It's called mathematical induction. We're not going to talk about this one today, but I want you to have it in your list of arguments, ways to prove things, and we will talk about it later. And then I already mentioned this one, but maybe it didn't get into your notes, and I've got it written in actually in here, so we will make sure it gets in there one way or another. To prove that biconditional, that P if and only if Q, you must both prove P implies Q and Q implies P. And that means that the proof has twice as much work as a traditional implication kind of proof, right?